All right, let's go ahead and start up. What we're going to do this morning is wrap up the last part of the overview of concurrency and parallelism. If you recall before, I talked about what concurrency was. I talked about what parallelism was. I gave some examples of the history of concurrency and parallelism in Java through the ages. And what we're going to do now is we're going to wrap up the discussion by evaluating the different mechanisms that Java provides for concurrency and parallelism. So the key point of all this stuff is to understand what the mechanisms are and when to apply them, because there's a bunch of different choices. So if you recall, the concurrency and parallelism mechanisms in Java span multiple layers in the software stack. So there's some things that occur down at the operating system kernel level. We haven't really talked about those at all. These are things like low-level threading mechanisms implemented in C. There's system libraries that provide wrappers for those things, again, below the level of abstraction that we're talking about in this class. Then we get to where we start to talk about there's some mechanisms that are available at the execution environment layer, which is things like the Java virtual machine or the various execution environments you get with Android. There's concurrency and parallelism frameworks and Java threads and synchronizers that occur at the Java class library level. And then there's additional stuff on top of that, which is, again, beyond the scope of what we're covering here. So the question arises, whenever there's multiple choices, which are the best choices? And as usual, the answer depends on what it is you're trying to do. So if you're trying to build performance-sensitive applications, things like maybe video games or mobile games, then you want to choose certain mechanisms that have very low overhead because you don't want to incur delay or add additional jitter to your experience by users. Likewise, if you're trying to build lower-level classes, the intent of which is to provide the basis for higher-level frameworks or higher-level mechanisms, you might want to stick with these low-level mechanisms, which are the ones provided with shared objects. So things in Java util concurrent, which we will not talk too much about in this course. We'll talk about this in a different course. These are the mechanisms you might choose if you're trying to stay with the lower-level stuff. And if you want to learn more about Java util concurrent, there's some nice descriptions of Java util concurrent at this video by my friend Doug Lee, who talks about how it's designed. So examples of these mechanisms would include things like reentrant locks, or semaphores, or condition objects, or countdown latches, all the kind of nuts and bolts synchronizers that are available in Java. So the good part about using the low-level mechanisms are that they're efficient and very lightweight. They're intentionally designed to minimize overhead. The downside is it's rather tedious and error-prone to program at this level because you have to be responsible for sharing objects, and you have to make sure that you put the right synchronizers in. You have to think about things like atomicity and visibility and ordering and all this low-level stuff, which we're really not going to talk much about in this class. So shared objects are typically best used by infrastructure developers, people building software infrastructure as opposed to people building apps. And that distinction is particularly important in layered environments, layered platforms like Android, where you can see that you've got many different layers. The higher up in the stack you go towards the application layer, the more likely you are to want to use the higher level stuff, which we'll talk about in a second. The lower down you go, the more you might want to use the infrastructure stuff. And the reason for that, of course, is that if you make things really inefficient at the lower layers, everybody suffers. Whereas if you program at the application level, you're mostly concerned often with human productivity, programmer productivity, as opposed to trying to wring out every last nanosecond from the performance. But at the infrastructure layers, it's more important to wring every last nanosecond out of the performance. So that's kind of one choice. If you're building lower level stuff, if you're building performance sensitive stuff, stick with the shared object approaches because they're most efficient and lightweight. So the alternative approaches, one of the alternative approaches are to use Java's message passing mechanisms. And examples of message passing, of course, would be things like, there's a couple different examples. You could use the sort of lower layer message passing mechanisms, things like the linked blocking queue or array blocking queue. That's kind of the basic way of having a thread safe queue where one or more threads can be producing work and sticking it on the queue, and one or more other threads can be pulling things off the queue and doing stuff with it. That's message passing. And if you take a look at the frameworks which are developed on top of these lower level message passing mechanisms, you'll see that there's lots of good examples of that. Some of which we will cover in this course, most of which we'll cover in the next course. So examples would be things like the asynchronous task framework that Android provides, which gives you this very cool sort of programming model that you can have the tasks that you send work to be executed. There's also something called the handlers, messages, and runnables framework, or the hammer framework that's part of Android. We probably won't cover that very much in this class. We'll cover it more next semester. There's also some other things that Java provides, things like the executor service, the executor completion service, which are frameworks for doing coarse-grained task parallelism in Java. So the real focus there is on passing these messages around and decoupling the sender and the receiver so you can make them loosely coupled and more flexible and easier to compose. So the good parts about using message passing is that it's more flexible and more decoupled because you're not having to access these low-level shared objects directly. Instead, you're passing messages back and forth, so the degree of coupling in the software is minimized, so it's easier to mix and match stuff. The downside is that there's a bit more time and space overhead. Why is there more time and space overhead? Because you're typically moving objects, moving tasks, moving messages, and so on from one thread to another. And whenever you do that, that will cause what's called context switching, which occurs when you take one thread that's running and you suspend its execution, and you then start up another thread. So when you have a producer thread and a consumer thread, if you don't have the ability to run them both in parallel on multiple cores, then there's going to be context switching to move from one thread to the other. Whenever you have to pass messages back and forth with some kind of message queue, which is what message passing is all about, of course, you need to synchronize access to that message queue to make sure you don't corrupt the state of the message queue. You have to worry about things relating to memory management and data movement, moving data from one cache to the next, and so on and so forth. So those things start to add up. Now, a lot of times it just doesn't matter because that's not where the bottleneck is in your code. So if you're doing software where you have a number of cores and the amount of time it takes to do the work on whatever task you're passing from one producer thread to a consumer thread is fairly long, then the fact that there's this additional overhead is really in the noise. So unless you're really building performance-sensitive apps, probably not a big deal. Okay, the third type of approach, which of course is what we're going to focus on in this class, will be using higher-level frameworks. So these would include things like Java streams and parallel streams and completable futures and RxJava, which is yet another framework built on top of all these lower-level mechanisms using functional programming features and facades and so on. And those approaches are most appropriate if you're an application developer and you're just trying to get your app done very quickly without having to wrestle with all the lower-level mechanisms. So assuming you know how to do functional programming, assuming you know how to do or you know how to use these frameworks, building your apps will often go much faster and be more scalable because there's less to worry about. So that's a good thing. And of course, that's what we're going to be doing in this class. So you'll be doing a whole pile of different implementations of this image crawler program, and you'll get a chance literally to see the pros and cons of each approach in terms of its complexity, in terms of its performance, and you'll be able to visualize it very quickly once we start moving away from the sequential versions to the parallel versions. You'll see it running faster, especially if you have a multi-core laptop or phone, because it'll go way faster. So the pros of this approach, the pros of using the highest level frameworks, are that you become more productive as a human being because you don't have to spend as much time wrestling with these low-level concurrency and synchronization mechanisms, which are tedious and error-prone. Your code will hopefully become more robust because you won't be wrestling with these issues, so the accidental complexities won't creep into your solutions. The downside, of course, is that these frameworks also add overhead. It doesn't come for free, and they are a bit prescriptive. So if your program fits nicely into a model of decomposing some big task into lots of small subtasks and running those subtasks in parallel in a MapReduce-like approach, then these higher-level frameworks are your cup of tea. But not everything fits into that Procrustean bed of design. So if you don't have the ability to map your problem into this MapReduce-like world, then these frameworks could be problematic. Having said that, honestly, the Completable Futures framework, which is the coolest one of all, which we'll do at the end, that one is usually very, very productive and very efficient. But it's a little bit more complicated to program. So you kind of have to get trade-offs between these things. OK, so the key point to take away from all this stuff is that to be a coveted full-stack developer, which is what we should all aspire to if we want to go off and do software these days, you should understand the concepts and the mechanisms at each of these different layers. So, at the very least, knowing from kind of the execution environment layer up is important. Not necessarily, you don't necessarily have to understand how the operating system kernel works at the lowest level, because chances are you will never program that anymore. Most people these days are not, certainly people are not programming operating system kernels by and large. You might find a person from time to time who might write a device driver, maybe, probably not. Most people, however, are users of layers of software from, sort of on top of the execution environment up. Very few people are even doing things at the execution environment layer anymore. So these are sort of the layers from sort of the orange layer of concurrency and parallelism frameworks up is where you spend most of your time. However, it does pay, literally pay, because you get more money, the better off you understand the layers in the stack. And you'll often see advertisements these days looking for a full stack developer. Now, what that typically means, usually, is somebody who can do front-end programming with, I'll use the word modern in quotes because it seems like a throwback, but modern user interface frameworks like Angular or React Native from a GUI point of view, and then also be able to handle sort of the middleware part and the database part. So that's kind of a full-stack developer, front-end, back-end kind of thing. I personally think that JavaScript is an abomination. It's horrible, but we're stuck with it, at least to some extent. OK, so that is the end of the discussion of concurrency and parallelism in Java. At this point, you should know enough to be able to answer quiz questions, but obviously to really program these abstractions, these layers, these frameworks, and so on, will take more than just what we've covered heretofore.